Hello, good evening. This is Turbomachinery BDE 40303, semester 1 2023 and 24, group project report. For the group member, the first one is Erickson Amen, and the second is Mishki Yahya, third one is Muhammad Zuldi, fourth is Siti Nazira, and for the fifth is Nur Izati. So we are from group C, section 1 under lecturer Encik Suzairin. So this is introduction. For the first one is turbine are mechanical devices converting fluid energy to mechanical energy in industrial processes. And second, radial flow turbine are specific type with a widespread use in power generation, aerospace and fluid handling. And also turbine are crucial in power generation propulsion and various industrial fluid systems. So as you can see from figure 1 and figure 2. And here I will be explaining about the working of a radial flow turbine. So the first one is the inlet. The working fluid enters through the central inlet and moves towards the turbine blade. And second, the acceleration. The fluid gains velocity and kinetic energy with the blade designed to accelerate it radially, inducing rotation. And for the third one is expansion. Flowing through the blade, the fluid expands, leading to decreased pressure and temperature. So this expansion accelerates blade rotation and produce more mechanical energy. And for the fourth one is outlet. The fluid exits the turbine through the outlet for discharge to the atmosphere or subsequent processing. So for our project, for this assignment, our task is to design a new radial flow turbine that can efficiently extract energy from a river flowing water. Considering the volume flow rate of the system, which falls within the range of 0.03 to 0.09 meter cube per second, while adhering to the specific limitation outlined in table 1.1.
My name is Nur Izati binti Zulkarnain. I will explain to you about the design specification. So this study introduced limitation on various parameters, which is flow rate and inlet absolute angle to guide the design process. We use the same flow rate, which is 0.05 meter cube per second, and the same inlet absolute angle alpha 1, which is 10 degree. So the ultimate goal is to compare 3 sets of data, which each set comprising of 10 calculations. So for set 1, we use a different parameter for inlet blade angle, which is from 100 degree to 160 degree. Then all the other parameter will be constant. Next, for set 2, we use different parameter for inlet blade width, which is B1 from 0.005 meter to 0.03 meter. All other parameter will be constant and we will calculate the power shaft. And lastly, for the set 3, we use different parameter for inlet blade radius R1, which is from 0.3 meter to 0.5 meter. All other parameter will be keep constant and we will calculate the power shaft.
Hi and Assalamualaikum. My name is Siti Nazira binti Muhammad Yunus. My number matric is DD200067. So I will continue with the design analysis. So for the design analysis, we have 3 sets. So for this set is to change the inlet blade angle, which we have 10 calculation for each set. So for this set 1, I will present for one example only for the inlet blade angle, which is 100 degrees. So the Q flow rate is 0.05, the alpha 1 is 10 degree, the beta 1 is 55 degree, B1 0.01 meter, B2 0.015 meter, and the R1 0.4 meter, and the R2 is 0.12 meter. So this parameter is fixed for 10 calculation. So to calculate the power shaft is the formula is W dot shaft equal rho Q multiply U1 V theta 1 minus U1 V theta 2. So to calculate the U1 is V theta 1 minus VR1 divided by tangent 80 degrees, and to calculate the V theta 1 is equal to VR1 divided by tangent alpha 1. So we can get the VR1 from the formula VR1 is equal to Q over A, And then we can get U1 and V theta 1. To calculate U2, we need omega. So from the U1, we can get the omega, which is for this set is 27.323 radian per second. So, and then we can get the U2. So we can get the VR2, V theta 2, which is U2 minus VR2 divided by tangent beta 2. And then we can get the W dot shaft is equal to 6133.95 watt. So for set 2, we change the inlet blade width. So I will show the one example only out of 10 calculations. So for this example, I choose P1 as 0.005 meters. So for the parameters, which is Q is 0.05, the alpha 1 is 10 degree, the beta 1 is 110 degree, the beta 2 is 55 degree, B2 0.015 meters, R1 is 0.4 meter, R2 is 0.12 meters. So to calculate the power shaft is also the same from the set 1, which is the formula is W dot shaft is equal to rho Q multiply U1 V theta 1 minus U2 V theta 2. So to find the U1 and V theta 1, we can calculate first the VR1 and then we can get the U1 and V theta 1. And then to calculate U2, we find the omega first, which is the 52.795 radian per second. And then we can get U2 and find the VR2 and V theta 2. So, and then we can get the power shaft, which is 22,801.49 watt. So, next. So for this set, we change the inlet blade radius. This set is also have 10 calculations. So I will show only one example, which is this example. I choose the R1 is 0.3 meters. So the parameters is Q is equal to 0.05. The alpha 1 is 10 degree. The beta 1 is 110 degrees. Beta 2 55 degrees. B1 0.01 meter. B2 0.015 meter and R2 is 0.12 meters. So this parameters is fixed for 10 calculation. So the power shaft is also the same calculation from set 1 and set 2. So the formula is W dot shaft is equal to rho Q multiply U1 V theta 1 minus U2 V theta 2. So to find the U1 and V theta 1, we first calculate the VR1 and then we can get the U1 and V theta 1. So to calculate the U2, we need to find the omega first, and the omega we get is 46.93 radian per second. So after get the U2, we can get the VR2 and V theta 2. So the power shaft for set 3 is 9,878.25 watt. So that's all from me. Thank you.
Assalamu alaikum. I'm Mashak Yahya. I'm going to discuss how we conduct our project. So the aim of the project is to design the radial flow turbine with highest power output. So we have to find best design that help for the turbine, radial turbine, to extract the energy from the river. Yeah. So how we did that? We did 30 calculation for 3 sets. The first set is 10 calculation. In this first 10 calculation, we change the inlet blade angle and keep the other parameters in constant. We don't change the other parameters. We only change the inlet blade angle. The second 10 calculation, we change the number of blade width only. And the third 10 calculation, we change the we only change the blade radius and keep the other parameters constant. So after this calculation, we find the highest power output is 22,000 and 793.79, and that happened in set 2 when we changed the inlet blade width. When we reach the inlet blade width of 0.005 meter, we get the highest efficiency, the highest power output. So that indicates that the lowest number of inlet blade width gives the highest energy output. And we also do 3 graphs. The first graph, it was about the uh, inlet blade width against the output, the power output, and the second graph is about the inlet width blade against the power output, and the third graph is about inlet blade radius against the power output. I'm going to explain it in next slide. So for the first graph, as you see in the screen, in the figure 1, that the graph shows the increase in the inlet blade angle and decrease in power shift. And that's mean when the inlet blade angle increase, the power output of the radial flow turbine decrease. This can that's mean the larger blade angle result in increased resistance and decrease in the efficiency of the turbine. In figure 2, in the second graph, the relation between the inlet blade width and power output. The graph showing that the increase in the inlet blade width result in decrease in the power shift. And that means the larger blade width lead to increase the drag and reducing the efficiency and overall of power generation. As shown in figure 3, in graph 3, showed that the increase of inlet blade radius decrease the power shift of the power shaft. And that's mean we increase the blade radius, that will help to higher losses to increase frictions and turbulence. Ultimately diminishing power generation. And we can conclude our discussion by saying that the increasing in the inlet blade angle and width and radius all negatively impacted on power output due to high resistance and drag and losses, and that lead to reduce the overall efficiency. And the importance of selecting the optimal values for these parameters to maximize the power generation and enhance the turbine performance.
Assalamualaikum, my name is Muhammad Zudi Bazadali and I will present for conclusion. In conclusion, the study emphasized the crucial role of choosing the right parameters for radial flow turbine design to maximize power generation and efficiency. Especially a smaller inlet blade width was found to significantly boost turbine performance. Graph illustrates consistent trend showing that increasing blade angle width or radius had negative effect on power output due to increased resistance and losses. Overall, the findings contribute to a clearer understanding of radial flow turbine design and stress the importance to precise parameter selection for optimal performance across different water flow rates.